Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 9 academic students who are studying the Measurement and Geometry unit. Part 3 of that unit is a look at optimization, and this is video number 2 on optimization. In the last video, we defined optimization and what it means for the mathematical world, and we did an exploration in which we looked at how to maximize an area given a certain perimeter. So this was the question that we did in video number 1. We were told that a farmer wants to make a rectangular enclosure for his sheep and that he had 600 meters of fencing for the enclosure. He wanted to optimize the rectangle. So we discussed the fact that optimizing a rectangle with a certain perimeter would mean that you want to maximize the area. No one ever wants to minimize the area. That just doesn't make sense. So if you know a certain perimeter, then your goal is to maximize the area. And what we discovered is that the optimal area, or the biggest area we can make, is 22,500 square meters. And that was found when the length was 150 meters and the width was 150 meters. And then, of course, our little smart sheep guy noticed that 150 meters by 150 meters is in fact a square. And make sure you know a square is in fact a rectangle, so I'm not cheating. A square is just a fancy rectangle. So the fact that it's a square is not a coincidence or just true to this question. The fact that a square is the optimized shape is kind of the point of what we're learning in these videos. So we started to look at a second question, so let's start that again and see where we got. It says a contractor is pouring cement to create a rectangular playground. After the cement dries, the area will be surrounded by an expensive fence. The total area of the playground is to be 240 square meters. What dimensions would minimize the cost of the fencing? So obviously a word like minimize should make you think about optimization, because if you're minimizing or maximizing, you are optimizing. Now, I know that the area has to be 240 meters squared. So that's obviously the limitations or the constraints of this question. I know the area. Now, if I'm minimizing the fencing, we know that fencing is a concept that relates to perimeter. You put fencing around an object, not in the middle of it. So we are trying to minimize perimeter given a particular area. Now again, it's a rectangle. And it's a rectangle with an area of 240 square meters. So here are some examples of rectangles that fit that criteria. So each of these has an area of 240, and you can check that quickly in your calculator. Length times width, length times width, length times width. They all have an area of 240 meters squared. Now that's just 3 rectangles. So using some spreadsheet software, I quickly found a whole bunch of other rectangles. And I said each of these rectangles has an area of 240 square meters because it has to. This question says you must have that area. So this rectangle could take on a whole bunch of different looking shapes, but all of these shapes are rectangles and they all have the same area. Now, what we're trying to do again is we're trying to minimize perimeter. So I then asked the computer to calculate perimeter for me. Of course, it's an easy enough calculation for us to do. 2 plus 120 plus 2 plus 120, or 2 plus 120 doubled, and so on. So you can see that all of these rectangles have the same area, but they certainly have different perimeters. In fact, they go from a large perimeter of 244 meters to 62 meters here in the middle. So even though they have the same area, they have different perimeters. And remember, our goal was to minimize perimeter. So which one do we want? Well, when you look at this table, it's pretty clear that the minimum perimeter we can see is 62 meters, and that occurs here. And if you look at the values of length and width for these two rectangles, length of 15, width of 16, those are awfully close to the same number. So these shapes are awfully close to perfect squares. They're rectangles, they're not quite perfect squares, They're more like squares than any of these other rectangles, and that's why they have the smallest perimeter. And again, if I were to graph the length of each rectangle and compare it to the perimeter, you can see that there's definitely a minimum value, and that once you start changing the length, your perimeter starts to increase in this direction and increase in this direction. So there is a perimeter, and it's right about here. Sorry, there is a minimum perimeter right about here, and every other perimeter is going to be larger than that. So it looks like there's a tie for optimal perimeter at 62, and the dimensions are 15 by 16 or 16 by 15. And they're both very close to squares. And that's perfectly fine, but I've got this guy here, and he wants a perfect square. I don't know why, but this is what he thinks. He wonders what dimensions would actually create a square, and what would the perimeter be then. So pretty close to a square, but not perfect. Could we make it a perfect square? So what we know again is that we're making a square. This time we're forcing it to be a square, and I'm doing that by giving the length and the width this exact same measurement by calling it x in both dimensions. So again, the area is 240, therefore length times width must be 240. So here's the math. Length times width is x times x, which is x squared, and the area is 240. So x squared equals 240. Taking this square root, I get a value for x of 15.49. So that means that the perfect square that I could create out of an area of 240 is 15.49 by 15.49. So up here, we had 15 by 16 and 16 by 15, and now we have something that kind of fits in between those at 15.49 by 15.49. Now, what would the perimeter of this perfect square be? So 15.49 times 4 would give us a perimeter of 61.96 meters. So we've saved, 4 centimeters in perimeter. Yeah, I know that's not a lot. And the reality is, if you're buying fencing, it's probably irrelevant. But I just wanted to show you in the theoretical mathematical perspective that we can get even smaller than we had if we made a perfect square. So let's summarize. We know that in between 15 by 16 and 16 by 15, we could create a perfect square if we made the dimensions 15.49 meters and 15.49 meters. That would give us a perimeter of 61.96 meters. Not a lot less, but still absolute minimum perimeter. And again, the absolute minimum is a square. And that is the point of this lesson. Here it is, and I showed you this in the first video. The optimal rectangle is a square. The optimal rectangle is a square. So if we want to maximize the area and the perimeter is known, make a square. If we want to minimize the perimeter and the area is known, make a square. In other words, anytime you have the word rectangle and maximize, make a square. If you see the word rectangle and minimize, you make a square. So here's some questions to try to see if we kind of get that idea. And I'm just going to warn you, I've thrown a trick right in the first question, just to see if you're thinking. Here's what it says. Which dimensions produce the smallest perimeter for a rectangle area of 120 meters squared? Well, obviously, the word smallest is like the word minimal or minimum, and therefore this is an optimization question, and it's about a rectangle. So you know already that you should be thinking about a square. But I warned you there was a trick. Do not think that therefore the answer is C, because C is a square. You're right, C is a square, but look what I said. I said you have to have an area of 120 meters squared. What would the area of this rectangle be? 15 times 15 is not 120. So C, even though it's a square, does not have the right area. Oops, I hope you didn't answer that one. So let's check and make sure that the other ones all have the right area, and then we can see which one best answers the question. So 5 times 24 is 120. 20 times 6 is 120. 12 times 10 is 120. So none of the other ones tried to trick us with their bad area. So the question is, which one of these rectangles is closest to a square? Well, obviously, the more alike that the dimensions are, the closer it is to a square. So the answer would be D. This is the one that's closest to a square. The next one says, Amanda wants a rectangle with a, a perimeter of 100 and the largest possible area. So again, keywords rectangle and the word largest. You know you're optimizing, so you know that we should be thinking about a square. Now I need a perimeter of 100. So let's go through and not be fooled the way we may have been in question 1. Let's check the perimeter of each of these rectangles first, then we'll see if something's a square. Now a rectangle that's 10 by 10 would have a perimeter of 40. 10 plus 10 plus 10 plus 10 is 40. I need a perimeter of 100, so it's definitely not that one. A rectangle with the dimensions 20 and 30. So 20 plus 30 plus 20 plus 30 is 100, so that's fine. What about this one? So 25 plus 25 plus 25 plus 25, yep, that would work. 40 plus 60 plus 40 plus 60, no, that's not the right perimeter. So I'm down to only 2 choices, and one of them is a perfect square, so obviously my answer would be C. Another question to try. What are the dimensions of the rectangle with maximum area that also has a perimeter of 500? Well, you can see I've already drawn the square for you because rectangle and maximum, you should know by now it's a square. Now in this case, the square has to have a perimeter of 500 centimeters. And I want to know what the length and width are. So don't forget that a square has 4 sides and each side is the same length. So we'll call it x. So x plus x plus x plus x has to add to 500. So you could say that 4x equals 500, and therefore x equals 150. Therefore, the dimensions are length equals 150 centimeters and width equals 150 centimeters. So I just took the perimeter and I divided by 4, and that gave me a rectangle. Actually, that gave me a square, which is also a rectangle. Next one. What are the dimensions of the rectangle with minimum perimeter that also has an area of 150 millimeters squared? Well, a rectangle with minimum perimeter, we know we have a square. Now this time I know the area. The area is 150 millimeters squared. And again, I also know that I have a square. What are the dimensions? So length and width are both x because they're the same value. And the area is length times width. So length times width is x squared. So in this case, x squared equals 150. So I'm going to need to take the square root of 150 to figure out what x must be. And the square root of 150 is 12.2. So that means the dimensions of this square must be length equals 12.2 millimeters and width equals 12.2 millimeters. So once you get the idea that you have to make a square if you're optimizing a rectangle, it's just a case of working with the information you have. Now, I do want to make one little comment about when you do optimization in grade 10. In grade 10, you're going to be doing optimization again, and you're also going to be working sometimes with fences, but you're going to have different questions than this. You're going to do things like building a fence, but using the barn as one side of the fence. So something like this. So you're still going to build a fence and you still want maybe the optimized area, but this time one of your fence walls doesn't have to be built because you're using a barn. Now in this case, the answer is not a square. It's something else entirely. Well, sort of, but you'll see in grade 10. So I just don't want you to walk into grade 10 and think a square, a square, a square, because sometimes there are different things that could happen. Anyway, that's the end of this video. See you in the next one.